All right. Good morning, everyone. So we'll get started. The rest of the class might join us later. If you haven't sent text in the chat, please do so I can take that as attendance later. Okay, just say hi or good morning. So we'll be still looking on the geometric optics today. So and then I hope we can cover enough content so we can have the lab that associated with this one has the content cover. Okay, so the lab this week will be the last lab of this class on imaging. Okay, so some part of today's lecture will cover that at least. Okay, so let's take a look on what we have covered earlier from this chapter last time. So the first section of the chapter talks about the ray aspect of light. So basically, you can use the ray array to indicate the propagation of light through a homogeneous media. Okay, so if the media is homogeneous, then the light will travel in the straightforward direction. Okay, then you can use a line with the arrow to indicate the direction of the traveling of it. Okay, so a lot of times you will be dealing with geometry and using a little bit of trigonometry knowledge here for the optics. Okay, the first one, the law of reflection here, it talks about the incidence angle formed by a light with the normal direction is equal to the reflected angle that the reflected ray makes with the normal direction. Okay, so that's law of reflection, theta I equal to theta R. And the next section talks about speed of light. So basically, speed of light in vacuum is close to 300 millimeters per second. Okay, and as the light enters the medium, transparent medium, then the speed of light will be reduced by a factor called index of refraction. So the if you do speed of light divided by the speed of light in vacuum divided by the speed of light in the media, then that gives you index of refraction. Okay, c is the speed of light in vacuum, and then v is the speed of light in media. All right. So with that, when the light enters from one media to another media, so then the angle or the direction of the propagation of light actually will change. And this is can be described by Snell's law, which says index of refraction in one media times sine of the incidence angle equals to index of refraction times sine of the reflected angle. Okay, refracted angle theta 2. All right, so n1 times theta 1 equals to n2 times theta 2. Now, if you are going from thicker media to thinner media, which means if the light goes from a media that has greater index of refraction to a media that has less index of refraction. Okay, so as you increase the incident angle, the refracted angle, according to Snell's law, is going to be bigger than the incidence angle. So at certain point, when the incident angle is greater enough, so then the theta 2 is going to reach 90 degrees first. Okay, so when that happens, after that, then the light will not go through the second media, the thinner media. Okay, it will undergo total internal refraction, so it will just reflect it back into the media itself. Okay, so then this angle, we call it critical angle. Okay, so you can calculate it from by looking at Snell's law, set n2 to be equal to 90 degrees. Okay, so then you can solve for your n1, which will be the critical angle. All right. We also talk about dispersion of light. So if you have a mixture of light going through a media, so because different light have different wavelengths or different frequencies, so then the index of refractions actually varies a little bit. Okay, so index of refraction is depends on materials. It also depends on the color of light you have. Okay, because they vary a little bit in frequencies. Okay, so then index of refraction also varies due to you have different light. Okay, so if the white light is a mixture of 7 different colors hits this prism at the same angle, then different lights will come out at a little bit different angle. That's so then you can separate the lights. Okay, that's how we can see rainbow. Okay, because the air drop in the water drop in the air actually separates out the different lights from sunlight. Okay, so then we see different colors in the air. Also, when it's not raining, so typically this will happen in some in fall. Um, so and then in the afternoon, okay, so you will see that sometimes in the sky when the sun is going down, say probably like 2 or 3 hours before it actually sets. So then you'll see a circle around the sun. Okay, so that's actually because in the air there's small ice cubicles or ice crystals. All right, so that actually reflected the sunlight. Okay, and then sometimes you see 2 bright spots over there. Okay, those are called sun dogs. Okay, so if the eyes are not homogeneous, they oriented in the sky. Okay, that's what you see. All right. All right, so let's take a look example on the dispersion here. So this one says if you have index of refraction for red light in a certain liquid, okay, that is 1.305. Now the index of refraction for the violet light in this liquid is actually 1.336. It asks you to find the dispersion, which is the difference in the angle that the 2 lights come out of the media. Okay, so it's the difference between the 2 angles. So let's take a look here. It's assuming that the instance angle is 45 degrees, okay, for each of the light. Okay, so let's draw a picture here to see the problem, okay, to visualize the problem. So let's say this is the air, okay, on top this is a liquid at the bottom here. Now this is the normal direction at where the 2 lights hits. Okay, so 45 degree to the normal. So this is 45 degree. All right. Now the red light has a smaller index refraction, so that will be deflect smaller. Okay. So if this is the original direction of the light, okay, then the red light will be diverted less than the violet. Okay, so the red light probably comes out at this angle, but violet might be coming out from this angle. Okay, I don't think I draw them in according to scale because this angle should be a small angle in difference of the 2. Okay, so let's call this as the angle for violet, and then this guy is the angle for the this guy here is the angle for the red. Okay, it's from the normal to the refracted ray. Okay, all right. So then we will just apply because we are looking for theta v minus theta r. Okay, so then we need to know theta v and theta r. So we can apply Snell's law twice, one for theta v, one for theta r. Okay, so n1 sine theta 1. So this is theta 1. All right, that should equal to n2 sine theta 2. Okay, so this is theta 2. We will pick theta v. All right, here. Now we should also use the index of refraction of 2 for the violet. So n2v. Okay, let's take that n2v here. Okay, now you might wonder that an index of refraction in air should also a little bit different from violet to red light. That's true, but because index of refraction in air is very small, okay, so even if there's a difference, this difference will be very small. All right, so we can just assuming that the 2 will have the same index of refraction in air. Okay, both are will be very close to 1. Okay, so you can also use 1 as approximation here. All right, so I'm going to just use n1 as 1 here then. All right, so then in this case, this is 1, so 1 times sine of 45 degree is equal to n2v for the violet light is 1.336 sine of theta v. Okay, and then I will be solving for theta v. All right, I'll divide both sides by 1.336. Okay, then I have just sine of theta v on the right. Okay, so I will take sine inverse to both sides to get rid of sine here. Sine inverse of sine theta v here equals to sine inverse of the sine 35 degrees divided by 1.336. Okay, so then on the right hand side, this is just theta v, and then if you do this in your calculator, it's going to tell you that this angle is 31.956. Okay, now because the difference in the two angles will be very small, so it's good that you keep extra digits here. Okay, so the problem gives the numbers in 4 digits, so I will keep 1 extra digit, so I'll keep 5 digits here. Okay, now this is theta v. Now we need to look for theta r, so we apply Snell's law another time. N1 sine theta 1 equals to N2 r, okay, sine theta r. Okay, so you'll be doing the same thing here. I'm going to just use 1 here, so on the left hand side it's just sine of 45. Then this is 1.305 for N2r sine of theta r. Okay, so my theta r then will be equal to sine inverse of sine 45 degrees divided by 1.305. Okay, instead of 1.336, now you change that to be 1.035. That gives you your theta r. Okay, the refracted angle for the red light. Okay, so this will be 32.809 degrees. Okay, so then the difference of the two angles, you'll be just doing theta v minus theta r. Okay, theta v minus theta r, 31.956 degrees minus 32.809 degrees. Okay, it's going to be minus 0.853 degrees. Okay, that's the difference, okay, of the two angles. All right. Any questions you guys might have? If you do, just unmute yourself and then you can speak up. Okay. All right. So if not, then we'll move on here. So we are going to look at the images formed by mirrors. Okay, so the focus will be on spherical mirrors, but that's take a look first the plane mirrors. Okay, so for plane mirror, you can actually use ray diagrams, so which basically a ray diagram is what you use to visualize the image, okay, formed by a mirror or a lens. So in this case, if you have an object here, the flower here, with the vase over here, so then you can actually take the top of the object here. Then for the top of the object, you can draw 2 rays, okay, hits on the mirror here. And then because you have plane mirror here, you can apply law of reflection. So then there will be 2 rays from the top of the object here comes to your eye, okay. Now you will back extend the 2 rays, okay, they will intercept somewhere behind the mirror. Okay, now because the ray, they do not actually go behind the mirror, so we use dashed line, okay, to indicate that's back extended. Okay, so then arrive at this p prime. Okay, this then will be the image of the top of the object. Okay, you can do the same thing to the bottom of the object here. Draw 2 rays, hits the mirror, and then you apply law of refraction, so reflect angle should be equal to incidence angle. So then there will be 2 rays coming into your eyes, okay, back extend, then the 2 rays will meet virtually behind the mirror here. So this then will be the bottom of your object. Okay, so this is how you actually utilize the law of refraction to form the image. Okay, so looking at the geometry here, if you look at one particular ray over here, hits this point and then hits the eye over here. So this angle, theta, that's the same, the two same angles, okay? And then this angle over here, this should be also theta because this line is back extended and then this is a horizontal line, okay? So when the two lines, they intercept, the two angles on one side should be equal to the other side, okay? So that's the same theta. So then phi should be equal to phi, okay? So then this is the identical triangle here to this guy here, okay? So then you can figure that DO should be equal to DI, okay? So that's one property of the image formed by plane mirror. The distance from the object to the mirror should be equal to the distance of the image to the mirror, okay? All right, so we'll take a look on spherical mirrors, okay? So a lot of times we are using spherical mirrors, okay? So for example, at the corner of a building, so sometimes you'll see a mirror on the wall, so it's actually a spherical mirror, okay? So that actually divert the light, okay? So then you can see the object that is across the corner, okay? Or like the side mirrors of your car and then the rear view mirror, they are all actually spherical mirror, okay? The curvature is so small, so you probably don't notice that it's a curved mirror, okay? They are curved mirrors, okay, actually. So for a curved mirror, usually it's a spherical mirror. It's a small part of a sphere that's being cut out, okay? And then one side of it is mirror. Either inside of it is mirrored or the outside of it is mirror, okay? So if the outside is mirror, then it's called convex mirror. If the inside is mirror, it's called concave mirror, okay? So you'll take a look on the two spherical mirrors here in this section, okay? For both cases, for a convex mirror or a concave mirror, okay? So they both have a principal axis, okay? So that is the line goes through the center of curvature to the middle of the mirror, all right? That's called the principal axis. And then they both have a center of curvature because they are both curved mirrors, okay? So those are two terminologies we want to introduce first. All right. Now, because the mirror is curved, okay, so there will be a focal point where, okay, if parallel rays hit the mirror, okay, then the rays will converge at a same point called focal point. Or if this is a convex mirror, if the outside is mirror, then the rays are diverged. But the diverged ray, if you back extend, then they will meet at the behind the mirror at the same point. Okay. So either way, there's a focal point for the mirror. Okay. Now, from the geometry here, so if we look at a convex mirror or concave mirror here, which the inside is mirrored, okay? So if you draw parallel rays to the center of, to the principal axis here, so then these rays hit the mirror, they will meet at the focal point when they are reflected, okay? So this is called focal point, all right? Now, usually, the center of curvature will be very large. Then the part of mirror, the whole length of mirror compared to the radius of the curvature is small. So then this angle theta will be very small angle theta, okay? So then from the center of curvature to the focal point, the distance is going to be equal to from the focal point to the mirror over here according to a geometry here. So because this theta is equal to this theta, okay? So, and because this is parallel to the principal axis, so then this angle over here should be also theta, okay? And then the fact that the theta should be small, okay? So then this length should be equal to this length or equal to this guy, okay? So this is from the geometry, all right? So then for the focal length of a mirror, it's going to be equal to 1/2 of the r, okay? for a concave mirror, it's 1/2 of R. For a convex mirror, it's minus 1/2 of R. Okay, so to determine either it's a positive focal length or negative focal length, it's based on if the mirror has the ability to either converge the rays or diverge the rays. Okay, so if the mirror can converge the rays, then it's called you have positive focal length. Okay, if it actually diverge the rays, the parallel rays, then it's having negative. Okay. All right, so then for a convex mirror, it actually diverges the parallel rays to the principal axis. So then you have minus as focal length. Okay, if you have a convex mirror, the mirror actually converge the parallel rays to the principal axis. So then the focal length is 1/2 R positive. All right, and then if you are not specifically told that it's a mirror, it's a convex mirror or concave mirror, you can determine the nature of the mirror by looking at the focal length. Okay, if it's positive focal length, then it's a concave mirror. If it's a negative focal length, then it's a convex mirror. Okay. All right. There are 3 principal rays you can use. Okay, so to find the image produced by a concave mirror. Okay, so the parallel ray, which is parallel to the principal axis, okay, they will reflect through the focal point because all of the parallel rays will meet at a focal point. Okay, so parallel ray will reflect through the focal point. The focal ray, that is the ray goes through the focal point, actually will reflect parallel to the principal axis. Okay, and then the center of curvature ray will reflect back along its incoming path, because if the ray goes through the center of curvature when it hits the mirror, then it's the normal direction. Okay, so let's take a look on these 3 principal rays on the figure here. Okay, for parallel rays, we sometimes just call it P rays. So parallel ray, that means this guy is parallel to the principal exit. Okay, so then it will go through the focal point because all parallel rays will converge at focal point. Okay, and then focal ray, the ray goes to the focal point, will reflect backwards. Okay, so this is actually reverse of the P rays. Okay, so if you have ray goes to the parallel ray, then it will be reflect parallel to the principal axis. Okay. Center of curvature ray, so you can see if this hits the mirror here, goes through the center of curvature, hits the mirror here, then this is the normal direction at this point. It will reflect back. Okay, so instant angle equal to 0, the reflect angle should be also equal to 0. So it just go backward. Okay. For any object, any point on the object, you can use these 3 rays to determine the image of it. Okay, but 2 should be sufficient enough to determine the location. Okay, so pick 2 rays, and then of these 3 principal rays, then you should be able to determine the location of the image. Okay, and then you always can use a third one to double check. Okay. If you have a convex mirror, okay, you can also use the 3 principal rays. Okay, but keep in mind, because the convex mirror, they don't converge the rays, but actually the back extent of rays reflected by the mirror from a parallel ray will go to the focal point. Okay, so then you'll draw this like this. So when the parallel ray hits the mirror here, it will reflect. Okay, but in the direction, if you back extend it, that will go through the focal length. Okay, but the center of curvature should hits the mirror and come backwards, because backward in the same direction, path, because that's the normal direction. Okay, so that's still true. And then for the focal ray, now it's not actually going through the focal point, but it's the ray that appears to go through the focal ray. Okay, so then that will reflect backward parallel to the principal axis. Okay, so a little bit differently, due to the nature that it actually the convex mirror will diverge the rays, but about the same. Okay, it's similar but a little bit different. You want to notice the difference. Okay, so for a concave mirror, all right, it has the ability to diverge rays. So it actually depends on the object, where the object is sitting at. Okay, so you can have 3 different kinds of images. Okay, depending on where your object is. Okay, so if your object is beyond the center point from the mirror, okay, so it's this over here to the left of the center of curvature here, then you can use the 2 rays. You can use parallel rays, you can use focal rays. Okay, you can determine the image should be formed over here when the 2 reflected rays meet over here. Okay, so you can see the image now is smaller than the object. Okay, and then it's inverted. Okay, and then the 2 rays, they do meet somewhere here. Okay, so then this will be a real image. That means if you put a screen over here, you should be able to capture the image over here, somewhere over here. Okay, now if you move the object closer to the mirror, in between the center of curvature and the focal point over here on the right shows here. Okay, again, use 2 principal rays. When the parallel ray hits the mirror, it will reflect through the focal point. Okay, when the focal ray goes through the focal point, hits the mirror, will reflect parallel to the principal axis. Okay, so then the 2 reflected rays will meet somewhere here. All right, in this case, you can see the image is actually larger than the object. Okay, but again, inverted. All right, and then the 2 reflected rays, they do meet over here. So that means this is a real image. Again, if you put the screen over here, you should be able to capture the image. Okay, all right. Now, if you move the object even closer to the mirror, all right, so the object, if you move the object inside the focal length, okay, between the focal length and the mirror over here. Now you can see if you draw a focal ray, okay, if this ray, if you back extend, it goes to the focal length, hit this guy, will go back, reflect parallel, okay, backwards. And then if you draw a center of curvature ray, will go this way. Okay, so the 2 reflected rays, they do not meet. Okay, 2 reflected rays, they go towards the left, they do not meet over here. But if you back extend them, they will meet somewhere here behind the mirror. Okay, so then when the 2 rays come into your eyes, it appears like it's coming from the image over here behind the mirror. Okay, so in this case, then you can see the image is actually behind the mirror, and then the 2 reflect rays, they do not meet. But if you back extend the 2 rays, they meet behind the mirror. So that means this is actually a virtual image. Okay, it's not a real image, because if you put the screen behind here, there's no rays meet over here, so there's no image over here. It's a virtual image. Yeah, it's a virtual image. It's not a real image. Okay, so in this case, you can see the image is enlarged. All right, it's upright. Okay, it's a virtual image. Okay, so for concave mirror, you can see depending on location of your object, you could have virtual image, you could have the real image, you could have enlarged image, you could have shrinked image. Okay, so depending on locations. All right. Now let's take a look on the mathematical relationship between the distance of the object and then the distance of image. Okay, so so take a look on the left figure here. Okay, if this is your object, okay, if it has a height of HO, which means the height of the object. Okay, so you are beyond the center of curvature, away from the mirror here. Okay, so then your image should be, as we discussed earlier, should be somewhere here. It should be a shrink image, a real image over here. Okay, so let's call the distance from the object to be from the object to the mirror to be DO. Let's call the distance from the image to the object to be DI. Okay, so in this case, and then the height of the object to be HO, the height of image should be HI. Okay. So you can see here, if this ray hits the mirror, reflected back, will go into the image over here. So this angle, according to law of reflection, theta should be equal to theta, okay? Then this little triangle below the principal exit, and then this larger triangle above the principal exit, they are two similar triangles, okay? Because they are right angle triangles with one angle being the same, then they are similar triangles, okay? So with the left figure, you can write the equation according to the um, similar triangles. All right, so for the similar triangles, you can write that if you do HI over DI, that should be equal to HO over DO, okay? So the height over one side is going to be equal to the height over one side, okay, over on the other triangle, okay? So that's a similar triangle. Now, if you have this one, you can rewrite this. So then if you do, or you can write HI over HO should be equal to DI over DO, okay? This can be rewrite from this equation, or this can be coming from the from the similar triangles, okay? Also, let's look at on the right figure here. Now, if you draw a ray that goes through the center of curvature, it should also go through the image, okay? So then in this figure over here, you'll have two little triangle shaded area here. So then the angle, they are right angle triangles, and then with one angle being equal to from one triangle to another triangle. So then these two triangles, they are again similar triangles, okay? So with that, you can write another equation of if you do HI over this distance, okay, which should be the radius of the curvature minus the distance of image, okay? Then it should be equal to HO over this guy, okay, which is DO minus R, okay? So we can write that. We can write that HI over R minus DI is equal to HO over DO minus R. Again, we can rewrite this. So we can have HI over HO equals to, so if you do HI over HO, that should be equal to R minus DI over D minus R, DO minus R, okay? So R minus DI, DO minus R, all right? So from these two equations, we can see HI over HO, HI over HO on the left, they are the same. So then on the right-hand side from equation 1 should be equal to the right-hand side from equation 2, okay? So then DI over DO should equal to R minus DI over DO minus R, okay? Now, this is a concave mirror, so then F equals to 1/2 R, okay? Or you can write R equals to 2F. All right. So then if that's the case, you can replace R with 2Fs. So then DI over DO equals to 2F minus DI over DO minus 2F. Okay. Now we are going to do cross multiplication. Or from this equation, you already see the relations between DI, DO, and the focal length. Okay, so it's all in this equation here. But we are going to simplify this equation. Okay, so we are going to do cross multiplications. All right, and then see what we get at the end. Okay, so cross multiplication, that means DI times DO minus 2F equals to DO times 2F minus DI. All right, cross multiply, basically multiply both sides by the denominators from the left, and then multiply by the denominator from the right. Okay, that's what cross multiplication does. Okay, all right, so if you are doing this, then you have on the left hand side you have DI DO minus twice F DI equals to twice DO twice F DO minus DO DI. Okay, now we are going to move this to the right, and then this turn to the left. So we'll have 2 times di times do, because minus becomes positive, that equals to 2f times di plus do. Okay, because this is 2f do, this is 2f di, so if you add the 2, it becomes 2f di plus do. All right. So from here you can see 2 and 2 can cancel out, and then if you divide both sides by f, you get rid of f from the right. Okay. Now if you divide both sides by dido, you get dido on the left. Okay. So then what you have now remaining is, on the left you only have 1 over f. Okay. And then on the right you have di plus do divided by di times do. Now you can separate the two. Okay, you can do di over di do plus do divided by di do. Okay, so then di goes away, do goes away. All right, so then you have 1 over f equals to 1 over do plus 1 over di. Okay, so this is simplified relationship between image distance of image to the mirror, distance of object to the mirror, distance of image to the mirror with focal length. Okay, with this simplified equation. All right. So this is called the mirror equation. All right, and then although we derive this from the concave mirror, but it also applies to the convex mirror. All right, but keep in mind, for a convex mirror, the focal length will be negative. Okay. All right. Any questions you guys might have on this derivation? Okay. So now let me see. Let me add something right over here. I don't have a slides for this, but for a convex mirror, because it actually diverges the parallel rays, okay, or the rays, if they are not parallel, if they come in a certain angle, the reflected ray come up will be also diverge. So then the angles, reflected angles are larger between the two rays, okay? Or the difference in the two reflected rays angles are larger. So in that sense, for a convex mirror, you will not converge any rays. So then the image formed by a convex mirror is always going to be a virtual image, because the reflected rays will never meet, okay, on the same side of the mirror for a convex mirror. So it's always going to be a virtual image, and then it's always going to be reduced in size. It's upright, okay. Doesn't depend on the location of the object. It's always going to be virtual, reduced image, and upright. Okay, so for the mirror hanging on the wall of a corner of a building, it's going to be a convex mirror. And then the mirror, the side mirrors in your car is going to be a convex mirror. All right, the rear view mirror in your car is also a convex mirror. Okay, so that's why if you look carefully, there's a print on your mirror button usually says the image appears smaller than it actually is. Okay, that's because it's a convex mirror. It has reduced size. Okay, but for concave mirrors, depending on location, you could have real image, you could have virtual image. Okay, if you have real image, it's always going to be inverted image. The virtual image is always going to be upright image. Okay, now for a real image, it could have reduced in size, it could be having the enlarged. Okay, or at some extreme locations, for example, if you are sitting, if the object is sitting on the center of curvature, then it will have the same size as the image, will have the same size as the object. Okay, you can do this, you can draw this if you have a good drawing, you can see that. Okay, And then if you are just beyond the F, okay, focal point away from the mirror, then it's approaching infinity. Okay, that's going to be a real image. But if you are just inside the focal point, okay, then it's going to be also approaching infinity, but it's a virtual image, it's an upright image. Okay, all right. Now another thing we want to talk about is the magnification of the image compared to the object. Okay, so this is simply defined as the height of the image divided by the height of the object. Okay, and then it's also going to be equal to minus of di over do. Okay, so you can see from the few images, um, it's from the similar triangles. Okay, the one we use, the two figures we use to derive the mirror equation. Okay, so if you check on those two pictures for on the triangles, you'll see the hi over ho is going to also equals the di over do. Okay, and then with a negative sign. Okay, because you'll have for real image, because it's inverted. Okay, so then the magnification will be negative. Okay, in that sense. All right, but we'll talk about the signs of these quantities. Okay, so the signs conventions here, if the f is positive, that is for concave mirror, f will be negative for convex mirror. Okay, and then m is positive for upright image, so that means magnification is positive for virtual images. Okay, and m is negative for inverted image. Okay, because you are inverted, so then we have negative for the sign for the magnification. Okay, so for real image, m is going to be negative. Okay, the image distance is image distance is positive for image that is in front of a mirror. Okay, so that refers to real image. If you have image in front of a mirror, then you have real image. Okay, if you have image behind the mirror, then you have virtual image. Okay, so then in that case, di is negative. Okay, so for a convex mirror, you always have di as negative. Okay, now for concave mirrors, if your object is within the focal length, then di is also negative. All right. Object distance do is positive for object in front of mirror, and then do is negative for object behind the mirror. Okay, so for the last one, this is about if you have multiple mirrors. Okay, then you can sometimes you can use the image in a mirror as the object for a second mirror. Okay, so but we are not going to deal with that complicated scenario here. Okay, in this class. All right, so we'll take a look on one example here. This one says if you have a concave mirror produces a virtual image that is 3 times as tall as the object. If the object is 16 centimeters in front of the mirror, what's the image distance? Okay, and then what's the focal length of the mirror? All right. So for imagings, there are basically two equations to deal with. Okay, the first one is the mirror equation, the do 1 over do plus 1 over di equals to 1 over f. Okay, and then the second one will be the magnification, which is equal to hi over ho and minus di over do. All right, two equations. The third equation we don't usually use a lot, but it's just this simple equation that f equals to either r over 2 or minus r over 2, depending on if you have a concave mirror or a convex mirror. But these two equations apply to both concave and convex mirror. Okay, so concave, convex mirrors. Okay, both scenario. This guy is for concave. This guy is called convex. All right, let's take a look on this one. This one says if the object is 16 in front of the mirror. So that means this DO is equal to 16 centimeter in front of mirror. That means positive. Okay. It also says the image is 3 times as tall as the object. So that means HI over HO is equal to 3. Okay. So then that tells you now HI over HO is the M. Okay, so the magnification is 3. Magnification can be also described by minus DI over DO. So then we are looking at this guy here. We realize that then DI is equal to minus 3 DO, okay, from this relationship. So then DI is equal to minus 48 centimeter, okay? It's asking us, okay, that's the first one we are looking for. What's the image distance? Okay, so that's that one. We just solved that one. I didn't realize. Okay, so that's that one already. B is asking you what's the focal length of the mirror. All right. Now we have DO, we have DI. So then from the first mirror equation over here, first equation, mirror equation over here, you have DI, you have DO. Then you can solve for your focal length. Okay, so you're just plugging numbers on that one. So 1 over 16 plus 1 over negative 48 equals to 1 over F. All right. So 48 is 3 times of 16, so then you can multiply both the first term numerator by 3 and then denominator by 3. So 3 over 48 minus 1 over 48, okay, equals to 1 over F. This is then 2 over 48 equals to 1 over F, or 1 over 24 equals to 1F. Okay, so then F equals to 24 centimeter. Okay, so then we just solve for the focal length to be 24 centimeter, which is positive. That is consistent with that the mirror is being a concave mirror. Against concave mirror should have positive focal length. Okay. All right. Any questions you guys might have on this one? So if not, then we are going to move on here. We are going to check image formed by lenses. Okay, so image formed by mirrors, basically you are using law of reflection. Okay, now if you have lenses, lenses is made of by polishing one side of mirror of the of a media, a plastic media or transparent media. Okay, so if you can polish that, and then it's being a nice curved over here. So if this is concaved like this, you'll see that if there's an object here, or maybe better looking at the bottom picture here, if there's an object over here, you can draw two rays. Okay, center of curvature ray, then the incident angle will be 0, reflect angle should be 0. So then you just go right into the material without deflection. And then for the parallel ray, okay, you apply law of Snell, then you'll see that this guy will be converged a little bit. Then you'll meet the first ray in the media at some point here. Okay, so you can see it will meet over here. This is by applying Snell's law. Okay. So for a lens, it's going to be a material, plastic, transparent material. Okay, either having the size, one side being curved like this, concave or convex. You can imagine you can also come to a curvature like convex curvature on this side. Okay, so in that case, then the ray will be diverged. So then the image will form somewhere here. Okay, not inside the material, but somewhere here. All right. So that's typically how a lenses can be made of. Lens can be made of by having one side or both sides of the material, the transparent material, either convex or concave. Okay. So if you have convex, okay, on one side, all right. can have like this concave, convex like this. This side is more than this side, and then you can also have convex here. This is a plane here, or you can have a double convex on both sides. Okay, so these lenses, they are convergent lenses. Okay, if you have lenses like this, they are convergent lenses. So the rays will be converged by these lenses. And then you can have divergent lenses, which you can have concave meniscus over here, which one side is more than the other side, all right? And then with one side being concave side and then plane side here, this is called plano concave lens. And then this is double concave lenses, okay? So in this class, we only deal with the double convex lens and then double concave lens, or we just call concave lens, referring to double concave lens, and then convex lens, referring to double convex lenses, okay? Now let's take a look on the ray diagrams of the convex lenses, okay? So for convex lenses here, it's a convergent lens, so then parallel rays will be converge at a point which we call focal point. Okay, you can imagine this as being made of like just like a two prism like this. Okay, so put them here, so we will converge lenses, but because this is smoothly curved, so then it will focus on one point. Okay. For concave lenses, it will diverge the rays. So parallel rays comes here, will be diverged. But then if you back extend the rays on the other side, you'll appear to be coming out from a same point called focal point of the concave lens. Okay, and then this is similar. You can do that. Imagine this is like many small pieces of prism and put in this configuration. Okay, so then you actually diverge the rays, the parallel rays. All right. Similar to mirrors, spherical mirrors, you can use three principal rays for lenses, okay, to locate the images lenses form, okay. So in this case, we'll have parallel ray again, parallel to the principal axis, okay, and then focal rays that is drawn either towards the lens or focal point or through the focal point, okay. And then this time we will not have a center curvature ray because but we are going to have a midpoint ray which goes through the middle of the lens, okay. So this guy will not be deflected, okay, similar to the center of curvature ray in the mirror cases, okay. All right, we'll look at images formed by the lenses, okay. So for convex lenses on the left here, parallel ray will hit the lens and then will go into the focal lens, okay, and then mid ray will just go right through, okay, and then focal ray going through the focal point on one side will be coming out parallel to the principal axis on the other side, okay. So these three rays you can use to locate where the image is formed by a convex lens, okay. Again, just two should be enough to determine that, but you can use the third one to double check, okay. On the concave lens case, the rays will come out diverged, but you can also use any two of the three principal rays to determine the location of the image, okay. You can use a parallel ray will appears to be coming out of focal point here, okay, on the other side, so diverge in the other side in that fashion. Focal ray appears to be drawing through the focal lens will come back parallel, okay, or be deflected parallel, okay, and then a mid ray, okay. If you have a convex lens, so in this case, if you are having a lens, convex lens actually means a convergent lens, okay. And then in the mirror case, a convex mirror, that means a divergent mirror, okay. So the two are actually, for the terminology, they are actually having opposite properties, okay. Convex lens means convergent lens, concave lens means actually divergent lens. So this is a concave lens, so it's divergent. So you can see if your object is over here, then your image will be here by using the three principal rays, okay. So that's a virtual image because the ray deflected ray of the ray going through the lens actually they don't meet, okay, but if you back extend, then they appear to be meet somewhere here. So this is a virtual image, okay. So concave lens will form a virtual image. For convex lenses, again, depends on the location of the object. You could have virtual image, you could have real image, okay. So in this case, if you are beyond the focal length, then you'll have real image, inverted real image. If you are inside the focal length, you will have virtual image. Okay, upright image, virtual image, the same side on the as the object is from the lens. Okay. For the real image on the left hand side, you can have either enlarged image, you can have shrink image. Okay, so depending on locations. All right. So this is a summary table of the image formed by lenses. So case one, if focal length is positive, that refers to, again, a divergent lens, a convergent lens, okay? So then if distance of object is greater than the focal length, then it's a real image, positive DI, negative M, okay? So DI is on the same side as DO, so it's positive. Again, convex lens, if you have DO less than focal length, then you're going to have virtual image. DI will be negative, okay, because it's a virtual image, then DI is negative, and then the magnification is going to be positive, okay. On case 3, which is convex lens, you're going to have virtual image, then its DI is going to be negative, and then the magnification is going to be less than 1, okay. For thin lenses equations, you can do the same thing as what we did for the mirror equation, okay? So you are going to apply the, use the similar triangles, two pairs of similar triangles, and you are going to write two similar equations as what we did. I'm not going to repeat that derivation, but at the end, the thin lens equation is going to be exactly the same as the mirror equation. Okay, 1 over DO plus 1 over DI equals to 1 over F. And then the magnification is also the same. Okay, so that would be the thin lens equation. Some sign conversions for thin lenses here. So F is positive for convergent lens, negative for divergent lens, okay, as the same as the mirrors. Magnification is positive for upright image. Magnification is negative for inverted image, okay. DI is positive for real image. DI is negative for virtual image. DO is positive for real object. And then DO is negative for virtual object. So this refers to when we have multiple lenses. Again, it's not the focus of this class, okay? All right. I think we are going to stop here. So again, if you haven't sent text in the chat, which I will take as attention later, that it's the final time you can do that, okay? Otherwise, we'll just stop here, okay, in case if you don't have any questions. So I will see some of you guys in the afternoon for the lab. I think we have just covered enough content for the lab this week, okay? So see you guys later, okay, either today or Friday. Some of you guys I will see you again in the afternoon. Some of you guys I will see you again on Friday, okay? Have a good day, guys. Bye.